Hello everyone, welcome back to the Math Tutor, and today we're going to be talking about Euler's method, which is a numerical approach to approximating the particular solution of the differential equation y prime equals f of x comma y. So, first I want to talk a little bit about who Euler's method is actually named after. So it's named after Leonhard Euler, who is a Swiss mathematician who lived in the 1700s, and he was really brilliant. He popularized so many things, such as using the symbol that we use for pi, coining the term f of x to describe the y-axis of a function, coining the use of the letter I to represent the square root of -1 or imaginary numbers, and using coining the summation sign, as well as giving the current definition of the constant E, which is also known as Euler's number. So these are just a few of the things he did, but he did so much more in so many different fields as well. This is just what he did in kind of the math field. So next, what is Euler's method? So it's a method used to solve ordinary differential equations with a given initial value. So the equation for Euler's method is y sub n plus 1 equals y sub n plus h, which is the step size, and we'll learn a little bit about that in a minute, times the derivative of the function sub n. And then how to use it. So in a given problem, you'll know the value of the solution at x naught from the initial condition, as well as the value of the derivative at x equals x naught. And then from that, you can write down the equation of the tangent line at x equals x naught. And then we're going to do a couple examples to use the equation above to come up with unknown values. So here's example 1 of Euler's method. And I've worked out a simple example. So I'm going to walk you through how you actually use and apply Euler's method. So in this problem, we're given the function y equals x squared, and we're asked to find the y value when x is 1.5. We're also given an initial condition, the point 1, 1, and the step size h of 0.1. So the first thing you're going to want to do is find the derivative of the function that they give you. So using the power rule, put the 2 to the front, and then it's going to be x to the power of 2 minus 1, which is 1. So the derivative is just 2x. And then what you're going to do next is draw a table. So you're going to want to have n values, x sub n values, y sub n values, and then we're going to test the actual values afterwards to see how close it is to Euler's method, to see how effective it is. So in this function, we can make arbitrary n values, 0, 1, 2, 3, 4, and 5. And then x sub n is also pretty simple because the initial condition is 1, 1, so that gives us x sub 0 and y sub 0 as 1 and 1. Additionally, the step size, h, is 0.1, so that means that each x will increase by 0.1. So for 1, it'll be 1.1, for 2, it'll be 1.2, and so on and so forth. Now we have to find the y sub n. That is where the Euler's method equation comes in. So the Euler's method equation states that y sub n plus 1 equals y sub n plus the step size h times the derivative of the function at x sub n. So if we want to find y sub 1, we can plug in y sub 0, which we know to be 1 from the initial condition, plus the step size h, which we know to be 0.1, again given in the problem, times the derivative of the function at x sub 0. So we know x sub 0 is 1. We know the derivative is 2x. So if we plug in 1 into the derivative, we get 2 times 1 equals 2. So y sub 1 equals 1 plus 0.1 times 2, which is 1.2. We can solve for y sub 2, y sub 3, y sub 4, and y sub 5. So for y sub 2, it's going to be y sub 1, which we know to be 1.2, plus the step size, again, 0.1 given in the problem, times the derivative of the function at x sub 1. So again, we know x sub 1 is 1.1. We know dy dx equals 2x, so 2 times 1.1 is 2.2. 1.2 plus 0.22 is 1.42. Repeating this process for the next three, we have y sub 3 equals y sub 2, 1.42, plus the step size times 2 times 1.2, which is 2.4. So y sub 3 is 1.66. For y sub 4, we have y sub 3, 1.66, plus the step size, 0.1, times 2 times x sub 3, 1.3, which is 2.6. And that gives y sub 4 equals 1.92. And finally, y sub 5 equals y sub 4, 1.92, plus the step size, 0.1, times 2 times x sub 4, which is 1.4. So 2.8 times 0.1, and calculating that is 2.20. Lastly, we can see how effective Euler's method is compared to the actual values of the function. So plugging in the actual values, which the function is y equals x squared, 1 squared is 1, 1.1 squared, 1.21, and so on and so forth. And you can see how accurate these two columns are, how close y sub n from the Euler's method is to the actual value. Let's try a harder example. So here is a more challenging example. We have the function y prime equals x plus 2y. We have the initial condition where x is equal to 2 and y is equal to 3. And we're trying to find y when x equals 2.5. And the step size is 0.1. So again, setting up your table, just from what we're given in the problem, this is what we already know. We can make arbitrary n values, 0, 1, 2, 3, 4, 5. And then x sub n, we know x sub 0 from the point is 2 and y sub 0 is 3. We also know that the step size is 0.1, so our x sub n's are going to increase by 0.1 each time. Now, let's use the Euler's method equation to solve the problem. Using the Euler's method equation, y sub n plus 1 equals y sub n plus the step size times the derivative of the function at x sub n, we can come up with this equation. Now, the difficult part about this problem compared to the last one is that the derivative has x and y's in it. So for this value, we need to find the derivative at x comma y. So the derivative at x comma y equals x plus 2y. We have an initial condition where x equals 2 and y equals 3. So we can plug in 2 for x and 3 for y to get that value of 8. After that, it should be pretty smooth sailing. We're going to have y sub 1 equals y sub 0, which we know to be 3, plus the step size, 0.1, times this value, 8. And that's going to give us 3.8 for our y sub 1. Now let's solve for the rest of the problem. Let's use the same method we used to solve for y sub 1 for y sub 2 through 5. So y sub 2 is going to be y sub 1 plus the small step times the derivative of the function at x sub 1. So the derivative of the function at x sub 1 we have to plug in 2.1 for x and 3.8 for y. And then using x plus 2y, let's see if it'll focus. Using x plus 2y, it's going to be 2.1 plus 2 times 3.8, which is equal to 9.7. So y sub 2 equals 3.8 plus 0.1 times 9.7, which is 4.77. Next up, we have y sub 3. It's going to be y sub 2, 4.77, plus the small step times, let's plug in f prime of y sub 2, or x sub 2 and y sub 2, which is going to give us 11.74. So, plus 0.1 times 11.74 is going to give us 5.944 for y sub 3. Y sub 4 is going to be y sub 3, what we just got, 5.944, plus the step size, 0.1, times, let's plug in f prime of x sub 3, y sub 3. And that'll give us 14.188. So plugging that into y sub 4, we have 7.3628. And lastly, for y sub 5, we have y sub 4, 7.3628, plus the step size, times, let's plug in x sub 4 and y sub 4 to the derivative to give us 17.1256. And plugging that in to Euler or Euler's method equation, we have y sub 5 equals 9.07536. So here's the table, and I hope you can see the difference between this one and the first example. The only difference is that the derivative of the function doesn't just have x's in it, it has x's and y's. So we have to plug in the x and the y value when we're evaluating f prime of the point. I hope this video gave you a clear and basic understanding on what Euler's method is and how it works. Thanks for watching.